Okay, can you guys hear me now? All right, excellent. All right. Okay. So welcome to day 4 of randomized algorithms. Today, the first lecture is going to be doing a little bit of algebraic things. In particular, we'll start out with it's not the first thing is not an algebraic lemma at all, and rather a weight function lemma called the isolation lemma, which says the following. Suppose you have some universe U of size n, and you have a family of sets over this universe. If you, is it possible at all to see this screen? I should probably be doing this, right? There we go. All right. Can you guys see the screen? All right. So suppose you have a universe and you have a family of sets over this universe. And now you assign random weights to the elements of your universe. Then every set is going to get a weight as well, right? So the weight of a set is just the sum of the weights of the elements in it. Now you ask yourself, what is the probability that the set that has the minimum weight, or what's the probability that there exists a unique set that gets the minimum weight? Right? There could be more than, some sets will get the minimum weight, definitely at least one. There could be more than one. What's the probability that there's exactly one? And what the isolation lemma says is that if the number of weights you have is bigger than the universe, then with good probability, the minimum weight set will be unique, right? So if I have a universe of size n and I use 2n weights, then with probability at least 1/2, the minimum weight set will be unique. And this is something that should come a little bit of as a surprise, because neither the probability nor the weight function is a function of the family at all, right? Like, it seems like you take any family over universe of size n. If you pick a random weight function with probability at least 1/2, the minimum weight set will be unique. The proof of this is kind of cute, so I'm going to show it. I'm going to say that an element is critical, and when I classify it with respect to the family and the weight function. So suppose I give you a family over universe and a weight function for the universe, then I will say that I'll say that an element is critical if it appears in at least one set of minimum weight. However, if I took its weight and I increased it by 1, then the element would no longer be in any minimum weight set. Hey, it's a definition taken out of nowhere, but it's at least, it's hard to understand where this definition came from, but it should be fairly easy to understand what it is. So you're critical if you are in at least one minimum weight set, but if I increase his weight, then he's no longer in any minimum weight set. In particular, if you take an element and you increase its weight, then the weight of all the sets that contain that element also increase by 1. Right? And here's a cute claim, and that is that F has a unique minimum weight set if and only if no element is critical. So I'm not going to prove this. You're going to prove this. For now, I just want you to believe me that this is true. So I want you to believe that the family has a unique minimum weight set if and only if no element is critical. All right. So let's assume the claim and prove the lemma based on the claim. Right now, what we're trying to prove that if I pick a random weight function, then with good probability there is a unique minimum weight set. And in particular, that means that what I should be proving is that with good probability, no element is critical. So then, as we always do when we're trying to have some statement of for all elements they are critical, instead we look at one element and say what's the probability that that element is critical, and then we'll do union bound. Right. So what is the probability that a particular element is critical? Well, when we're assigning the weights are assigned independently, so we can pretend we assign weights to all of the other elements first, and then we're assigning the weight to U last. Right? Now, if I have assigned weights to everyone else, then I claim that there is at most one value from the possible weights that I could give to U to make it critical. Why is that? Well, suppose giving it weight I would make it critical. Right? Then I claim that for any smaller I prime, giving it weight I prime would not make it critical. Why not? Exactly, right? Because with weight I, it isn't a minimum weight set. For if I gave it weight I prime, then if I increase it a little bit, it would still be in a minimum weight set. Therefore, it wouldn't be critical, right? On the other hand, for every I prime bigger than I, if I gave him weight I prime, U would not be critical either. Why? Because it wouldn't be in a minimum weight set because it was critical at I, right? So it wouldn't be in a minimum weight set at I plus 1, and therefore at anything higher either. Yeah. So in particular, if some weight makes it critical, then no bigger or no smaller weights make it critical. So there is a unique critical point. Okay. But what does that mean? It means that the probability that U is critical is 1 over W, right? And now I union bound over all elements of the universe and get that the probability that there exists a critical element is the cardinality of U over W, which is just N over W, which is what we claimed, proving the lemma. Okay, so back to a problem we've looked at before, namely k-path. So you're given as input a graph G, an integer k, and the problem is, does there exist a simple k-path in the graph G, right? So is there a path on at least k vertices? We've already seen an algorithm with running time 2e to the power k. We've seen an algorithm that approximately counts k-paths in time roughly 2e to the power k. What we're going to do now is going to see a faster algorithm. We're going to see an algorithm whose running time is 2 to the k polygon. And this is quite interesting because, as we'll see later today, we'll be able to get a deterministic algorithm for k-path with running time 2e to the power k. However, at present, there is no deterministic algorithm for k-path known with running time 2 to the k. So, so we're going to now see a randomized algorithm, which we don't know whether it's possible to randomize it and get the same running time or not. Okay, so what I'm going to do now is I'm just going to throw a lot of definitions at you. And you just have to absorb them all. And so therefore, please slow me down. If at some point it's too much, then tell me to come back, talk about it again. Okay, so here we go. A walk is just a sequence of vertices such that every pair of consecutive ones have an edge. So in the walk, vertices can repeat. All right. What's a labeled walk? A labeled walk is a walk where I've additionally given a function from the positions in the walk to the natural numbers. So I'm saying, well, the walk says it first visits some vertex v1, v2, v3, v4 up to vl. And then I have a function sigma from 1 through l, the length of the walk, to the natural numbers, where sigma 1 equals 5 means that the first vertex gets labeled 5, sigma 2 labeled 3 means the second vertex gets labeled 3. So for example, here is a labeled walk. It starts at let's say this vertex, let's call him A, then it goes to vertex B, then C, then D, then B again, then E, then F, right? And so the walk is A, B, C, D, B, E, F, and the labeled walk would be A1, B5, C2, D7, B8, E2, F3. Yeah. Okay. Now, what does it mean for a walk to be multi-labeled? A walk is multi-labeled if this labeling function is a bijection from the length of the walk to the integers from 1 to the length of the walk, right? So if I just give every vertex a unique label from 1 through, if the walk is length k, then I give it unique label given the integers from 1 to k. So in particular, this walk has 1, 2, 3, 4, 5, 6, 7 vertices if you count them with multiplicities. So this walk is multi-labeled. Yeah. So a multi-labeled walk is a labeled walk where the labeling function is a bijection, and it's a bijection from the steps of the walk to however many vertices the walk uses with multiplicities. Okay. What's a multi-labeled path? A multi-label, or what's a labeled path or a multi-labeled path? Well, it's a multi-labeled or labeled walk where the walk is a path, so where no vertices repeat. Okay, so the concepts are path, walk, labeled path, labeled walk, multi-labeled path, multi-labeled walk.
From which set we are numbering?
The naturals.
Naturals. So.
Yeah.
The example of what will be multi-labeled path.
So the top one is the multi-labeled path, the bottom one is a labeled path. In this example, it's not a multi-labeled path, it's a multi-labeled walk. There is a subgraph that, yeah. No, but the important thing is that okay, here the important thing is the vertices of the graph are not thought to be labeled. It's not that I give you a graph with labels on the vertices. I give you a graph without any labels on the vertices, and now a multi-labeled walk or multi-labeled path is a pair that visits the vertices in some order and assigns labels to the visit. Right? It's like I'm walking to this vertex, and to this vertex, and to this vertex, and to this vertex, and then every time I visit the vertex, I pick a number. I'm free to pick whatever number I want. That's the label that I pick when I visit the vertex, right? So it's not the vertices are already labeled and I get to the label when I visit the vertex. It's when I visit the vertex, I pick a label. No, because because in the color coding, you're assigning the labels to the vertices, and then you're assigning colors to the vertices, and then the color of the vertex when the path visits it is always the same. Right? Here, the vertices aren't labeled, and every time I visit it, I'm going to pick, and it seems like a totally crazy concept. It looks totally useless at this point. So yes, but then it would be a labeled walk and not a multi-labeled walk. Yes, in a multi-labeled walk, when every step has a distinct label, yeah. So it's a function not from the vertices of the walk, but from the positions of the walk, right? Like a walk has position 1, 2, 3, 4, 5, 6, 7. It could be that the vertex visited at position 3 and position 6 are the same vertex, but they're still distinct positions, and therefore they should get distinct labels if it is a multi-labeled walk. Correct. Yes, so for paths, labels to assigning labels to positions and labels to vertices is the same, whereas for a walk it isn't, and that is actually a crucial ingredient of the algorithm.
What appears to us should be given to.
Correct. Yes.
Labeling the walks and the vertices of the walk or the position?
The labels are assigned to the positions of the walk, both in walk and path. Yes, so notice the definition of a labeled walk or multi-labeled walk is a walk. A walk is a sequence of vertices, and a labeling is a function from the integers 1 through L to the integers 1 through L. The interpretation is, I mean, it's just a pair, a walk and a function. I give it a picture interpretation, but a labeled walk is just a walk and a function.
And is it so whatever, since we are asking for permutations, that this function is a permutation in case of multilabel walk?
It's useful that it is a bijection. Yeah, so I mean, I guess it is useful. Yes, I mean, it is useful that it is permutation.
But if it was a larger set of something,
You'll see. Yeah. Okay, so can I proceed?
May I ask a question?
Yeah.
Is sigma the function corresponds to the walk, meaning the walk is fixed, and does sigma depend upon walk? And multi-labeled path, doesn't it sound confusing because it looks like actually it's unique labeling? These are two questions.
So okay. A multi-labeled walk. Okay, a walk is a sequence of is in a graph is a sequence of vertices, right? So, for example, if here I have a graph, let me give the vertices some names. Right. A, B, C, D, E, F, G. What is a walk? A walk, for example, C, D, E, G, E. This is a walk. It's not a multi-labeled walk because it's just a walk. I haven't given any labeling. Right? Now I have a function over here. Sigma from 1 through 5 to 1 through 5. Sigma 1 equals 4. Sigma 2 equals 3. Sigma 3 equals 1. Sigma 4 equals 5. Sigma 5 equals 2. This is a function, right? It's a permutation from 5 to 5. Yes? The pair W, comma, sigma is a multi-labeled walk. Now, if I change 5 to 4, for example, then W, comma, sigma is no longer a multi-labeled walk, but it is a labeled walk. If I put 4 and I change it back to 5, and now I change E here and I change it to F, then then this is not only a multi-labeled walk, but it is also a multi-labeled path. Yeah, and notice that the graph I'm considering does not have any labels on it. It's just vertices that have names. Yes, I mean, formally, the domain is just the number of vertices on the walk. Oh, sorry. Sigma 6 equals 6. Okay. Yes, there are 6 vertices on the walk, and you need to have as many. The function needs to have as big of a domain and range as there are vertices on the walk in order to be multi-labeled. In order to be labeled, the domain is the number of vertices and the range are the naturals. The number, yes, okay, thank you. The number of vertices and positions is the same for paths, but of course, it's not the same for walks. So for walks, what we care about is the number of positions. Yes. Yes, it makes a partition, but it's an ordered partition. So in particular, the multi-labeled walk that assigns it 1 the first time it visits and 5 the second time is not the same multi-labeled walk as the one that assigns it 5 the first time and 1 the second time, and we're going to crucially use it. Was did I answer the question from Zoom? Okay. Okay. So now that these definitions have settled, what we want to do is we want to apply the isolation lemma somehow on the multi-labeled k-paths of G. But in order to do that, we need to translate, multi-labeled k-paths into a universe and a family, right? If you've ever downloaded a library off the internet and tried to use it, right? Your stuff is not on the right format. You need to put it on the right format to apply the library function. This is what's going on. It's just that it's math, not the library off the internet. No. We want to give weights to multi-labeled paths. We haven't given the labels. We want to be able to assign weight. We want to be able to say, if I give you this multi-labeled path, this is what its weight will be. Yeah, so for every path, like for every multi-labeled path, I want to be able to say that's what its weight is.
But what I was asking is, you don't know where the multi-labeled path is coming from.
No, we don't know and we don't care. So far. Okay, so here's the universe. The universe has one element for every edge of G. And furthermore, for every vertex and possible label. So we're interested in multi-labeled K walks. So walks on precisely K vertices. So the set of possible labels will now be the integers from 1 through K. So our universe is the edges of the graph, union for every pair of vertex comma label. Yeah. And now, if we think of a walk as a set of edges together with a set of vertex label pairs, yes, then okay, we can't actually completely recover. I mean, there is not a bijection now between walks and sets, because if you go around a cycle twice, then you don't know which label you use the first time and which label you use the second time. But in a path, there is a bijection. So there is a bijection between paths and sets in the universe, right? So if I give you a multi-labeled path, and I tell you which edges did it use and which vertex comma label pairs did it use, then if I tell you the edge set and the set of labeled vertices, I can also tell you which vertices did it visit in which order and which label did it use when it visited the vertex. Yeah. So in particular, I'm going to say the following, that for a multi-labeled K path, I will define the set S of P corresponding to the path to be all of the edges on the path, together with VI, not sigma I, it should be sigma applied to I. Let me fix that since I'm sigma of I. Yes, for I in, so this, and of course this should not be S of P, it should be S of P comma sigma. Come on. There. Great. So if I give you, yeah. Pardon? What is the size of the universe? Well, how many edges does G have? M. How many pairs are there of vertex comma label? So no. So first we ask. The ask was the question was, what is the size of the universe? What is not what is the size of SP sigma? The question was, what is the size of U? Yes, and the size of U is just M, the number of edges in the graph, plus N times K. Yeah, for every vertex label pair, we have an element. So M plus N times K is the size of the universe, and the size of every set corresponding to a labeled path or multi-labeled path is K minus 1 for the edges plus K for the vertices with labels. Right? Yeah. It's well, it's a bijection between, okay, it's not really a bijection, it's an injection. This is what I mean. So if I tell you S of P comma sigma, you can uniquely recover P and sigma. This is what I mean. It's like, given S of P sigma, you can uniquely recover P and sigma. Pardon? Every vertex of the graph? No. Not necessarily, it's a K-walk. Yes? Well, then that vertex doesn't get a label. I mean, no, but we aren't in a, remember that a labeled walk is just a pair, a walk, and a function from the number of vertices in the walk, or the number of positions in the walk to the integers. So in particular, every position of the walk gets a label. There is no requirement that every vertex in the graph gets a label. Well, I mean, it's confusing stuff, so keep asking questions.
Additionality set S P comma sigma would be K minus edges in the path plus for every vertex in path there will be label, so it will be K plus 1 plus K.
Oh.
K minus 1 plus K.
K minus 1 plus K, exactly. The size of SP sigma is K minus 1 plus K. And yes?
That is what I'm asking. So I'm not getting where the labels are coming from. So are we saying that every K path in the graph all the K paths are multi-labeled K paths or something?
For every K path in the graph, there exist K factorial multi-labeled K paths corresponding to that path. They don't come from anywhere so far. This is just a definition.
Okay. All right. Are the edges of the path directed or?
It doesn't matter. It can be a directed graph, undirected graph, whatever you want. Okay, yeah, so this is a good question. So when you think of a path, I will say that the path and the reverse of the path is actually the same path. Yeah. So I will think of a path as a set of vertices and edges. And then as a set, I mean, I will just treat the path and its reverse as the same thing.
But then there'll be two possible.
No, if I treat them as the same thing, then there's only one. Right? I mean, if this is me, this is also me.
Yeah, but when you're giving the edges of P, like are you giving?
Yeah, so okay, you have a point in the sense that when I defined what is a path, I said a path is a sequence, right? Like a path is a sequence of vertices, and of course, the reverse of the path would be the reverse sequence. Yes, but when I say that given P and sigma, I can uniquely recover P, what I mean is I can uniquely recover P sigma up to reversal. Yes?
So, but for from left to right and right to left, is SP sigma will be different now.
No, from right to left and left to right, so here. Can you move me? I guess I can use the board here. No, can you do this? Okay. So suppose I have a path. So here's a path. A, B, C, D, and I give it labels 1, 4, 2, 3. Yes. Then what is P sig? What is the pair? P sigma, right? It is A, B, C, D coupled with the permutation 1, 4, 2, 3. Yes? What is the reverse of the path, right? Like what is the reverse of P sigma? It is D, C, B, A coupled with the permutation 3, 2, 4, 1. I'm free to define when I revert like I don't reverse the path. I reverse the labeled path. Yes. So when I'm saying the labeled path gets reversed, I also reverse the permutation.
In this example, can you just explain that what is this S of P comma sigma and how do you recover the path? Because
So what is S of P comma sigma? So so S of P sigma, yes. So let me call this the reverse. This was Q sigma prime, right? And I'm claiming that P and sigma are the same. So S of P sigma would be now AB, BC, CD, and then A comma 1, B comma 4, C comma 2, D comma 3. Yes, and S of Q sigma prime, not Q sigma prime is the same.
and what does it mean to recover the path from this? That
You recover the pair P sigma and Q sigma prime. Yeah. Yes, because P sigma and Q sigma prime are me and me reversed. Yes.
But SP sigma and SQ sigma will be different.
Yes, correct. SP sigma and SQ sigma will be different. Yes, exactly. Yes. Okay. All right. So yeah, so here is and again an example. Here is a P and a sigma in a Peterson graph, and this is what his SP sigma is. I guess we have already covered it, but let me cover it one more time. So if I do the path EAFIDC, then SP sigma will be the edges EA, AF, FI, ID, DC, together with the labeled vertex pairs E5, A1, F3, I4, D6, C2. Yeah. Okay. We defined U, we defined SPF. Now we can define the family on which we will apply the isolation lemma. The family on which we will apply the isolation lemma is simply the set of all SP sigmas where P is a K-path in G and sigma is a multi-labeling of it. So it's the set of all SP sigma for multi-labeled paths P sigma in G. Okay. We apply our isolation lemma. We pick a random weight function from the universe to 2 times the universe, and therefore by the isolation lemma, the probability that F has a unique minimum weight set is at least 1/2. Now, at this point, notice that we have broken symmetry between the different labelings of the same path, because now they have gotten potentially different weights. Yeah, so before they were all the same, but now we gave the vertex pairs different weights, and therefore the different labelings of the same path would have gotten different weights. Okay, yeah. Before, for every path, we had k factorial multi-labelings of that path that all looked the same. But now we have given the vertex label pairs different weights, which means that different labelings of the same path may have different weights. They don't necessarily have different weights, but they could. In particular, if I look at the unique minimum weight multi-labeled path, then all other labelings of it have higher weight. Okay, now what did we really do? We assigned weights to edges and to pairs vertex comma label. Yes. Now we used this weight function to give weights to our sets SP sigma. But really, we could also use this weight function to just put a weight on edges and vertex label pairs, which means that now the weight of a labeled walk is also well defined. So if Q sigma is a labeled, not necessarily multi-labeled, it's just a labeled walk that only uses the labels from 1 through k, then I will define the weight of that walk to be simply the sum of all of the edges used in the walk. I only use the weight once if I visit the edge once. Even if I visit the edge more than once, fine, I'll give it. Even if I visit the edge more than once, I'm going to use the weight only once. And if I use the same vertex label pair more than once, I'm going to only look at the vertex label pair once as well. But we will only be considering in the rest of the argument walks that are multi-labeled. And therefore, whenever you visit the same vertex multiple times, you will always visit it with different labels. So while this thing of removing duplicates for edges will be applicable in our setting, removing duplicates for vertex label pairs will not be. Okay, so we've now defined a weight function for walks and observe that for multi-labeled k-paths, its weight defined through the set and his weight defined directly on the graph are the same thing. Okay, so take a breather, ask some questions. I'm sure there is confusion. This or before that? One before? So we assign a weight function, we pick a random weight function from our universe that we just defined to 2 times the universe. Now that we have a weight function on the universe, that automatically implies a weight on the sets, right? The weight of a set is the sum of the weights of the elements it contains. Yes? But it's also a weight function on edges and vertex label pairs. Therefore, we can use this weight function to assign weights to labeled blocks. Every time you use an edge, you pay the weight of the edge. Every time I use a vertex label pair, I pay the weight of the vertex label pair, but I only pay it once, even if I use it multiple times. Yeah, I guess here in this definition, I said that if you're here, I'm saying that you're actually paid multiple times. It actually ends up not mattering. So
It's not a multi-labeled block, and for each which occurs twice, you take just once. Similarly, for the every vertex, if it has.
So in order to be, I will have to walk back on what I said, because if I want to be, I mean, the reason I'm being inconsistent is that it ends up not mattering. But it is hard to think of 2 different definitions at once. I'm aware of that. I've experienced this many times as an audience. So let's pick one definition and stick to it. And it's not going to be the one that I said before. Let me stick to the one in the notes. If you use an edge multiple times, then you pay for it multiple times, as I've written here, right? Because you're summing over all L, like you're summing over all positions in the walk. Yeah. And here again, you're summing over all positions in the walk of the vertex label pair at that position. So the weight of a walk is the weight of its elements with multiplicity now, but for a path, it still ends up being the same as the weight of the set, and that's really the thing that matters.
Are you allowed to use edges multiple times?
Yes. So in particular, if I have a triangle, right? Going around the triangle twice and using the labels 1, 2, 3, 4, 5, 6 is a multi-labeled block. Going back and forth 10 times, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, and, or up, if I count it all the way to 20, this would be a multi-labeled block. Okay. Now, what is it we're interested in finding? We're interested in finding a k-path. Instead of looking for a k-path, let's look for a multi-labeled k-path. When we look for a multi-labeled k-path, we might stumble on a multi-labeled k-walk instead. That's bad. So we're going to say that a multi-labeled k-walk is good if it's a path, bad if it's not a path. Okay. And now comes the lemma that is going to put everything together, because we know that for the smallest weight for which there exists a multi-labeled k-path, that k-path is unique. Yes? In particular, for that weight, the number of multi-labeled k-paths of that weight is odd, because 1 is an odd number. But for every I, the number of bad multi-labeled walks of weight I is even. I don't know why this disappeared from the notes. So the number of bad multi-labeled walks of weight I is even, and it's multi-labeled k walks because we're using k vertices. Okay, that's the claim. In particular, notice that as a consequence, for the minimum, if there exists a k-path, and the minimum weight multi-labeled k-path is unique, then for that weight, the number of multi-labeled walks will be odd. And if there doesn't exist a k-path, then for every weight, the number of multi-labeled k-walks will be even. Okay. So please parse the lemma statement and ask questions about the lemma statement, if there are any.
Can you state again what is good and bad?
Good, a multi-labeled k-walk is good if it's a path, and bad if it's not a path. So if at least one vertex repeats. Yeah. Okay. So here's the proof. So how do you prove that the set has even size? You give something with a fancy sounding name. You give a fixed point free involution from the set to itself. What on earth does that mean? You say that you take the elements of the set and you pair them up. And if everyone has a body and no one is a body of himself, then they're all in pairs and therefore the set is even. Okay? This pairing up is called a fixed point free involution. So in particular, this is a function from the set to itself such that no one maps to himself, no one is his own body, and my body's body is me. Yeah? Okay. All right. So let us now give, and it should be clear that if there is a fixed point free involution, then the set has even size. Okay, so now let's give a fixed point free involution from the set of all multi-labeled bad k-walks to the set of all multi-labeled bad k-walks. So let Q sigma be a multi-labeled bad k-walk of a particular weight. Okay. Now here's the thing, it's bad, right? That means that some vertex repeats, right? If it's Q1, Q2, Q3, up to Qk, there is some vertex that repeats. And then let's look at sigma. Well, it's sigma 1, sigma 2, sigma 3. Take the first pair Qi, Qj that repeats, right? So take the first vertex for which there is a repetition and take the first repetition of that guy. And then what you do, you look at the sigma the first time you visited and the second time you visited the same vertex and you flip it. Now notice, and that is my definition of the fixed point free involution. And now all we need to check is that this is in fact a fixed point free involution. Well, first, it's fixed point free because I actually change the sigmas. Yes, so I never map someone to himself. Now notice that for which flip I decided to do is independent of the sigma. It depends only on the walk, and I didn't change the walk. Right? So when I say what is the first pair that repeats, I'm going to find the same pair, and I'm going to flip, so I'm going to reverse it. So the body's body is me. Yeah, so it is an involution. And it maps from the set to itself. It maps from bad walks to bad walks because we didn't change Q. And it maps from bad walks of weight I to bad walks of weight I because we didn't change the weights. The vertex label pair, set of vertex label pairs that we have didn't change. Okay, so we proved the fixed point free involution. Therefore, the number of these things is even. Take a breather, ask questions. Yeah?
So, or what is this twice?
Yes, you flip the label of the vertex that appears twice first. So Qi and Qj are vertices on the walk, but that they're vertices that repeat. So in particular, it's the same vertex. So you look at the first vertex that repeats, and you look at the first repetition of that vertex. And you flip the label that it got the first and the second time that it got visited. So you're not changing the walk, you're only changing the labeling. Precisely because you don't change the walk, you only change the labeling, right? If I have A, B, C, A, let's see, let me not visit A twice. Let's see, A, B, C, D, B, C, A, for example. My first repetition and then my labeling is 1, 2, 3, 4, 5, 6, 7. What is the first repetition? It's B, comma B, right? B and B repeats first. So when I flip, I'm going to get 1, 5, 3, 4, 2, 6, 7. So now this is my pair. Okay, so now in this walk, what is the first repetition? Yes, it's still B and B. So what do I flip? I flip 5 and 2. And what do I get? 1, 2, 3, 4, 5, 6, 7. If you flip something twice, it comes back to where it was. Exactly. Okay. All right, so then let's continue. Okay. We checked that Z maps bad multilabeled K-walks to bad multilabeled K-walks because we don't change the walk. The weight of the walk is the same as the weight of after the flip because we don't change the set of pairs. It's fixed point free because you actually do a flip. And it is an involution because if you flip twice, you get back to where you were. Therefore, we have now proved the lemma. And as a corollary, it means that for any integer, then the number of multilabeled k paths of weight I is odd if and only if the number of multilabeled k walks of weight I is odd. Yeah. So here's an algorithm. Let's count the number of multilabeled walks of weight I for every I. If it's odd, there is a multilabeled k-path, so there's a k-path. If it's even, well, I don't know, right? But if it's even for all I, I'm going to report there is no k-path. Okay, so now what we need to count multilabeled walks of a given weight. Yeah, and now this is the kind of the same dynamic programming thing that we did for counting multicolored paths, except that in multicolored paths, when you visited the vertex had a color and you were using that color. Now when you visit the color, you get to choose which label it gets. Yeah, that's really the only difference. And we're counting walks, not paths. Therefore, we don't care who we've visited before. So we only need to care about which labels we have already used, because in order to be multi-labeled, we're not allowed to repeat the label. Yes? So I have a table, TVSI, where V is a vertex in G, S is a subset of the labels, and I is the current weight. And this is equal to the number of labeled walks of weight I ending in V, using each label in S once and using no other labels. Yeah, that's our function. Yeah. Okay. And all I need to do now is to give a recurrence for this, right? So TVSI, if I only have one label available, yes, then I just need to check whether giving the vertex I'm in the one available label gives me the weight of the walk that I'm counting. If it does, then there is one walk that does that, otherwise it's 0. So if S is a singleton and giving it that weight, giving it that label gives me the wrong weight, then I cannot do it. So the number is 0. Otherwise, I sum over all possibilities for who my predecessor was on the walk. You better be a neighbor of V. And now I count walks that use the labels from S minus S, ending in U, and that have weight I minus the weight of V to S. Oh, I forgot something. What did I forget? There is a mistake here. How do I define the weight of a walk? It gets weights for vertex label pairs and edges, and I forgot to subtract the weight of the edge. So I also need minus the weight of UV. And now I'm done. Okay, so in particular, the size of the table is 2 to the k times poly n. It's like poly for every subset of the labels. It takes polynomial time per entry to fill the table. So the total time for this thing is 2 to the k times poly n. Right? And what does the algorithm do? Well, it picks a random weight function from the universe to 2 times the universe. It tries for every weight from 1 through, the maximum weight a multi-labeled k-path could have. And it counts the number of multi-labeled walks of that weight. If it's odd, you say, yeah, there is a k-path. And if it isn't odd for any weight, you return no. And that's the algorithm. Okay, so we now will do another one, which we will do faster, but this is a good place to take a breather and ask some questions. The table definition, the universe definition. So the universe is the set of all edges in the graph plus the set of all vertex label pairs. Okay, so yeah. Why? Because it's not that the number of good multi-labeled walks is odd. We know that for the minimum weight, the multi-labeled path of minimum weight is unique by the isolation lemma. So that was the good event. So that is the good event that happened with probability at least 1/2, and the only reason that this is a randomized algorithm. But we're counting for every fixed weight. For every fixed weight, we're counting the number of multi-labeled paths of that weight, and we showed that the number of bad multi-labeled walks of every weight is even. If you look at the algorithm, what the algorithm does is, for I equals 1 to 2u to 2k, count the number of multi-labeled k walks of weight I. Yes, it doesn't count. So we don't know that the number of multi-labeled paths in the graph is even. Where in particular, this is the reason it's called the isolation lemma. You isolate one solution, and give it a weight so that it's going to be the unique guy of that weight. Okay, breathe in, breathe out. Now it's going to get easy for a little bit, and then it's going to get so crazy that even if you're not entirely following, it's still fine. Yes. Okay, so we're going to look at the Steiner tree problem. So what is the Steiner tree problem? It's a generalization of spanning tree. I give you a graph G and a subset T of the vertices that I call the terminals. So in a spanning tree, you just want to connect all of the graph together. In a Steiner tree, you just want to connect the terminals together. Yeah. In a spanning tree, you buy edges. Today in Steiner tree, we're going to buy vertices. So you can buy non-terminal vertices. And now the question, and when you buy non-terminal vertices, like when you buy some vertices, you get all of the edges incident to them. Yeah. So it will be clear in 5 seconds. So input is G and the set T of terminals. The goal is to find a subset S of the vertices that contains the terminals, such that the graph induced by this set is connected and the cardinality of the set is minimized. So in particular, I mean, you have to buy the terminals, and now you pay $1 for every other non-terminal vertex that you put into S, and you want to pay as little as possible. This is what I mean. Now, so far, all of the parameterized problems we've looked at, the parameter has been opt, right? Like, can I find a solution of size k running with running time like c to the k? So you might get the impression that that's the only kind of interesting parameters that are out there. That's not true. We quite often want to look at some problem, and then you measure the complexity of the input instance in something that seems completely unrelated. Yeah. So in particular, now we want to say that, well, for complicated graphs, we're okay to be slow. For simple graphs, we should be fast. And okay, now, what is today's measure of simple? We're going to look at graphs with bounded bandwidth. Okay, so what does it mean that the graph has bandwidth at most k? It means that the vertices are ordered, v1 through vn, with the property that whenever I have an edge in the graph, the distance between the two endpoints of the edge in the ordering is at most k. So for example, a path has bandwidth 1 because here is an ordering 1, 2, 3, 4, 5, 6, 7, 8. The distance between the endpoints is 1. A cycle has bandwidth 2. Here is an ordering of the vertices of a cycle, so that the difference between any two vertices that have an edge between them is at most 2. Now, the reason so today we're going to assume that the bandwidth ordering is given as an input. So technically, bandwidth is defined for a graph and an ordering of the vertices, and then the bandwidth of the graph is the minimum over all orderings of the bandwidth of the ordering. But for us today, we're just going to care about graphs with a fixed ordering, and I'm going to conflate the bandwidth of the graph with the bandwidth of the ordering that we have been given. The reason bandwidth is called bandwidth is that if you look at the adjacency matrix of a graph with a low bandwidth ordering, then all of the non-zero entries are going to lie in a band of width k around the main diagonal. This is what's going on here. Yep. This is the adjacency matrix of the cycle that we just saw. Now, here is something that I'm not going to tell you, but there is if I give you a graph of bandwidth k, there is a fairly simple dynamic programming algorithm that will solve the Steiner tree problem in time k to the k, bandwidth to the bandwidth. The reason for this, so let me just sketch the main idea, is that if I look at any consecutive subsequence of, I think, k plus 1, k vertices. If I look at any consecutive set of k vertices in my ordering, then that is a separator. There is no edge from left to right in the graph. Therefore, if I'm trying to find the Steiner tree, and I look at like what is the intersection of a Steiner tree with the left side of the graph, well, I mean, maybe there are some terminals here. So blue are the terminals, yes? And here I have some Steiner tree going around and doing stuff, yes? So now notice that the Steiner tree, so the shaded area are presumably the vertices that I selected into my partial, into my Steiner tree. And a Steiner tree, of course, should be connected, but the intersection of the Steiner tree with this prefix doesn't have to be connected yet. Yeah. Now, all I care about for the purposes of trying to complete this to a Steiner tree is, which vertices of the boundary have been selected into the Steiner tree and which haven't. What is the total number of vertices on the left that I selected? And furthermore, which vertices are already together in connected components? Yeah, like which vertices on the boundary are already together in connected components, which in particular means I need to guess a partition of the boundary. And from the guessing the partition, you get a very natural k to the k factor. Yeah. And because of that, it really seems that like there is no way to escape this k to the k factor. I mean, like things that have different partitions are really different. They aren't interchangeable. And if you have things with different partitions, it doesn't seem like, oh, I can just kick one of them out because I will be able to use someone else in its place. Yeah. So it really looks like for this problem, a k to the k algorithm is unavoidable. So in particular, with Socket and Daniel Marks back in, I think, 2011 or 12, for a number of problems that kind of looked like this, we were able to show that assuming the exponential time hypothesis, k to the k running time is unavoidable. But for a number of problems, including Steiner tree, we couldn't show it. And we were just like, why can't we show it? Well, it turns out we couldn't show it because there is a c to the k algorithm. So there is actually a running time for Steiner tree on graphs of bounded bandwidth with running time 2 to the big O of k, using this wonderful cut and count method. So we're going to see an algorithm, or at least a sketch of one, that solves Steiner tree on graphs of bandwidth at most k in time 2 to the big O of k, and in fact 3 to the k times poly m. And this algorithm uses the isolation lemma. Okay, so now here is where the pain starts. So let S be the minimum size of some solution S. Remember, a solution is a set of vertices. Yeah. Again, to define the isolation lemma, we need a universe and a family of sets to apply it on. This is actually going to be easy. The universe is the set of vertices, and the family is the set of all vertex sets of Steiner trees of size S. Yeah. I now pick a random weight function from the vertices to 2m, and so with probability 1/2, there becomes a unique minimum weight set, so a unique minimum weight spanning tree. Now, Steiner tree, sorry. Now notice that every Steiner tree of size S now has a weight, so Steiner trees have now both size and weight. And we really only care about their size. Their weight is only there to make sure that there is a unique one of the smallest weight. Okay, now comes the crazy idea. The crazy idea is the following. Instead of looking for a Steiner tree, let's count the number of pairs of sets, S1, S2, that are disjoint, such that their union contains the terminals. There is no edge from S1 to S2. And the weight of these sets is precisely I. And I guess I also want to make sure that S1 union S2 has size S, which is the size of the Steiner tree I'm looking at. Okay? And now think about it like this. Every set S of a given size that contains all the terminals will contribute, like all partitions of that set into two sets S1 and S2 will have the same weight and the same set size. So they're going to be counted, right? Like all partitions of it will be counted. So in particular, every set S, the number of pairs it contributes to, like S1, S2, is just 2 to the power the number of connected components of the graph induced by that set. Yeah, so if I give you a set that contains all, if I give you a set S that contains all the terminals and has weight exactly I and has size exactly S, then the number of pairs S1, S2 that are disjoint such that their union is precisely S, and there is no edge from S1 to S2, is exactly 2 to the power the number of connected components of G induced by S. Yeah? For a Steiner tree, S have to be connected. 2 to the number of 1 is 2. Yeah? So every Steiner tree will contribute 2 pairs, S comma empty set comma S. Yeah? Pardon? Yes, these are ordered pairs. Yes? Everything that is not a Steiner tree will contribute a multiple of 4. Yeah? 2 to the 2 is 4, 2 to the 3 is 4 times something, also known as 2. So here's the algorithm. For every I and S, let's count the number of pairs S1, S2 of disjoint vertex sets such that T is a subset of S1 union S2, no edge from S1 to S2, the weight is exactly I and the size is exactly S. If ever this is 2 mod 4, there's a Steiner tree of that size and weight. If it's 0 mod 4, you don't know. Maybe there is an even number of them, but you don't know. But for the minimum weight, there is exactly 1, so you're going to see 2 mod 4. Okay. So now all that's left to do is to count these things. Yeah? So what are we going to do? Well, here's the picture. We're just as for the, yes. Yeah, so it's, well, it's like subset equals. It can be equal, right? No, we do need to look at S1 union S2 being a superset of T, because we're trying to look for a set S which is a superset of T. Yep. Okay, so now how do we count these pairs, S1, S2? Right? We're going to do it by dynamic programming. So look at our bandwidth ordering and look at some prefix up to position J. Right? Look at the K last vertices from Vj minus K up to Vj, and now we know that there is no edges from the vertices before to the vertices after. So now all we want to do is we want to count, like, we want to group our pairs S1, S2 into equivalence classes. So what we want to do is we want to look at what could the intersection of S1 and S2 with this prefix be, and we want to group them into equivalence classes so that everyone in the same equivalence classes can be extended by the same stuff to the right. Yeah. So what do you end up getting? you get some table with x, j, I, s, s1 star, s2 star, yes, which is what? Okay, I get the first one is the position, right? I'm looking at the prefix up to position j. Yeah. The second one is what is the weight of s1 union s2 so far? Yeah. The third one is what is the size of s1 union s2 so far? The fourth one and fifth one is what is the intersection of s1 and s2 respectively with these last k vertices. Yeah, and remember that s1 and s2 are disjoint, so we don't need to look at things that are not disjoint. So there is some sanity check that we can, and now we define this. Well, how many subsets of s1, s2 subset of the j first vertices are there such that s1 and s2 are disjoint, T intersection Vj, right, the first terminals are contained in s1 union s2. There is no edge from s1 to s2. Their weight is precisely I. Their intersection with the last part is precisely s1 star and s2 star respectively. Yeah. So we need some sanity check for s1 star and s2 star in order for there to even be any s1, s2 that you can do it with. So first they need to be, they can't overlap, right? Because if they overlap, then you cannot have an s1 and s2 that are disjoint. Yeah. There cannot be an edge from s1 star to s2 star because otherwise there will be an edge from s1 to s2. And if you look at any terminals that appear in these k vertices in the middle, then they better appear in s1 star union s2 star. Yeah. So I'm going to say that the pair s1 star s2 star are good for position j if they pass the sanity check. Well, now if we want to have a recurrence for if we want to have a recurrence for x, you basically go through a bunch of cases because what's going on is, let's see if did I draw a picture? No, I didn't draw a picture. What's going on is that you have the table for the previous position and you want to make the table for the next position. Yeah, and then really what's going on is that you need to decide. So when you have a recursive call for this position here, yes, you need to make recursive calls to this position here, which means that you need to decide, you need to not invoke anything that has to do with this vertex, and you need to decide on what to do with this vertex. Yeah, so now you know if s1 star or s2 star contains Vj, you might have to remove Vj and track its effect. And for Vj minus k minus 1, you might choose to either include it or exclude it, either from s1 or s2, or s1 star or s2 star. Yeah. So therefore you have 8 options, right? Like either you lose Vj or you don't, either you include Vj minus k minus 1 to s1, or you include it to s2, well, or you don't include it at all. So and then so that's 16 options actually, but I folded the 2 options of either you remove Vj or not into just 2 instead of 4. Okay. So let me remove this as well. So you know, here are the potential options, right? Like either Vj gets removed, either Vj minus k minus 1 gets added to s1 star or it doesn't, either it gets added to s2 or it doesn't, and then you just look at the different cases. I've written up cases 1, 2, 3, 4, 5, 6, and the first case is not applicable. Why is the first case not applicable? So the first case means that I should remove Vj from s1 star or s2 star if they're there, and I should add it both to s1. I should add Vj minus k minus 1 both to s1 star and to s2 star. So why is this case not applicable? Because they should be disjoint. Yes, and similarly, the same reason the 5th case is not applicable. Yes. Now, what is the recurrence for the first case? So there's the one where you remove Vj and you add Vj minus k to s1 star. Yeah, well, okay, then x j, I, s, s1 star, s2 star is equal to, well, you're looking at position j minus 1. Yeah, you're removing Vj, so now you should remove the weight of Vj from your weight budget. You removed Vj, so you should remove 1 from your size budget. And you're adding Vj minus k plus 1 to s1 star, so you add it to s1 star and you keep s2 star intact. Yes, and then, of course, finally you should do the sanity check, because if there is an edge between v minus j minus k plus 1 to someone who's already in, let's say, s2 star, then you shouldn't count this. Yeah, so you multiply it by 1 if s1 star, s1 2 star are good and 0 otherwise. Yeah, and okay, you go through all of these 6 cases, you make recurrences like this for each one of them, and this works out. Yes. Now, the important thing is, what is the size of the table? Yes, the size of, I have poly n for j, poly n for I, poly n for s, 2 to the k for s1 star, 2 to the k for s2 star, so 4 to the k, but s1 star and s2 star are disjoint, so for every element I can say it's either neither an s1 star nor s2 star, or it's an s1 star, or it's an s2 star. So for every element I have 3 possibilities, so my table has size 3 to the k, not 4 to the k. Yes, and if you look at what the recurrence does, it's never going over only subsets. There you just have some constant number of options. So for every table, you're actually spending constant time to fill it. Yeah, therefore the total running time ends up being 3 to the k poly n. Here is the algorithm. Pick a random weight function from the vertices to 1 through 2n. For every s from 1 to 2n, so for every size, and for every weight, compute the number of pairs s1, s2 such that their intersection is empty, they contain the terminals, there is no edge from s1 to s2, and the weight of s1 union s2 is I. If this is 2 mod 4, then you say there is a spanning tree, the Steiner tree of size s. And if you never find it, then you don't return anything. But of course, if we assume that the graph is connected, then you should find one at some point or other. Well, but it could be that you never find it because it's always even. So you could return fail in the end. So assuming that your isolation lemma succeeded, then of course you will always succeed. But I should have added a return fail in the end, and that happens with probability at most 1/2. Okay, so if algorithm returns s, there exists a Steiner tree of that size. If there exists a Steiner tree, then with probability at least 1/2, s will be at most t. Yeah, and that's it.
Second statement comes from this section.
Correct. So there are some questions in the chat, I think.
I have some vague. I mean, I lost the argument, but I just want to know whether the VIs are ordered such that the bandwidth condition.
Yes.
Is that a prerequisite? So.
Yes. So we are assuming that the vertices are ordered such that the distance between every pair of vertices is that are adjacent is at most k. Yeah. So we are assuming that the vertices are ordered like this in the input.
Okay. Okay. Yeah.
So let me make a remark, and that is that bandwidth is, of course, hard to compute. However, the algorithm that we just saw works for generalizations of bandwidth called tree widths and path widths, which are easier to compute, or at the very least, constant factor approximate in c to the k time. So even if the bandwidth ordering isn't given, you can get a c to the k, if not 3 to the k algorithm for graphs of bandwidth at most k, even when the ordering isn't given. And in fact, for even more general graph classes. That's well outside of the scope of this class, though.
Can you give some intuition on what problems we can try to do for applying this isolation lemma?
Oh my. Short answer is no.
I think it's just two problems like
So okay, so they're kind of, they're a little bit different. So in the first, so there's examples of a bit two different types of applications of the isolation lemma. I think maybe people who have a better understanding would be able to connect them. In the first one, you're using it to kill off hash collisions. So basically, like you're looking for some pattern somewhere, and you're trying to make sure that a vertex or something doesn't repeat. And you can use the isolation lemma to pair together things that repeat so that they cancel each other out, and then count things, without repetitions as things walks with paths. So instead of walks with paths, you could be looking for like a subtree, like for or something like this. So this motif finding, like for example, for finding cycles or finding motifs, I don't exactly remember the definitions. This kind of approach can be taken. And for the Steiner tree case, it's basically connectivity problems. So it's where you're looking for something like some vertex set or edge sets that satisfies some properties and is connected. So for example, this can be used to solve, like say, Hamiltonian path, because Hamiltonian path is find an edge set that gives every vertex degree precisely 2 and is connected. And it's sort of easy to look for vertex sets or easy to look for or count edge sets that give every vertex degree precisely 2, but they might not be Hamiltonian paths, they might just be cycle covers. But now when you say and is connected, then things become good, because this now is a Hamiltonian cycle. And now you can start pairing up, like doing like counting pairs of cuts, the way we did for Steiner tree, and end up counting, Hamiltonian paths mod 4. So there's this paper of Sigan et al. Called Cut and Count, which is there on arXiv, and also we do have part of a chapter in the Blue Book devoted to this. Okay, lunch. That's not my internet connection. Okay. All right. So can Zoom audience hear me? Good. Okay. So we've been talking about randomized algorithms so far, and you know, I said on day one that for the purpose of this class, randomized algorithms are algorithms. But you know, what's even better than randomized algorithms is deterministic algorithms. So now that we have some algorithms that are randomized, let's see if we can get similar running times with similar ideas and get rid of the randomization. And so we'll be able to do it for some, not far from all of them, but in this lecture, we're going to see two examples. So the very first one is the max cut problem that we considered in the very first lecture. So here input is a graph G. The task is to find a vertex set that maximizes the number of edges leaving the set. And we showed that if we pick a random vertex set, then the expected number of edges that are cut is half the edges. It's m/2. Now, here's an interesting thing. We could pick up our favorite vertex V, and we could ask, well, if we put V in S, or if we put V not in S, what would be the expectation of the cut if we assume that V is in S, right? In particular, we know that the expected size of the cut overall, just by the law of conditional probability, is the expected size of the cut given that V is in S times the probability that V is in S, plus the expected size of the cut given V is not in S times the probability that V is not in S. Okay, now let's do a check if you're all awake after lunch. What is the probability that V is in S? That's 1/2, right? So these are two halves and halves, right? Now here's a question. Okay, can we compute the expected value of the cut given that V is in S? Well, without any conditioning, we could use the method of indicator random variables. Let's try to use the method of indicator random variables just again. So XE is 1 if the edge is cut and 0 otherwise. And now what we're interested in knowing is, well, what is the probability that XE is 1, right? Previously, the calculation was the same for all edges. You had 4 possibilities of what could happen with each of the 2 endpoint vertices. Each one of these 4 possibilities happened with probability 1/4, and 2 of them cut the edge. Okay. So this still happens for all of the edges that aren't incident to V. But what about the edges that are incident to V? It's still 1/2 because V is always in S. The other endpoint is not in S with probability 1/2, which is when the edge gets cut. So we still actually have that for all edges, the probability that the edge is cut, given that the vertex V is in S, is still 1/2, which then means that the expected size of the cut, given that V is in S, is equal to the expected size of the cut given that V is not in S, which is still m/2. Which means that, you know, we can just greedily put V into S and nothing's really gonna change. All right. Now we put V into S, right? And you should think, okay, so it's like I see some puzzled faces here. Remember that whenever you have a cut, the complement set is an equally good cut. That's really what's going on, right? Like once you picked the first vertex, you broke symmetry. Yeah, but before you've picked anything, everything is completely symmetric. Yeah, so you might as well pick up your favorite vertex and put them into the cut. That's really what happened. Okay, now that we put V into S, let's assume that there is at least one edge, UV, such that V is an endpoint of that edge. Let's pick up some vertex U, which is a neighbor of V. And let's do the same exercise for U, but now conditioning both on the fact that V is in S, because we decided that V was going to be in S, and on the two options for what could happen to U. So, all right, we are now trying to figure out what is the expectation of D of S given that V is in S, which we know is M/2. But we can write it as the conditional expectation of the size of the cut given that both V and U are in S, times the probability that U is in S, plus the conditional expectation of the size of the cut given that V is in S but U isn't, times the probability that U isn't. And again, the times are all just times 1/2. All right. Now, yeah.
Sorry, I was question. When you say add B greedily to S, there isn't really a greedy choice being made.
Yeah, I mean the values are, I mean, greedily in the sense that you could do this, you could do that. You make an arbitrary choice. Yes. Yeah. Okay. Now let's try to compute, for example, the expected size of the cut given that both V and U are in S. Right? Again, let's do indicators, right? And again, let's try to figure out for every edge, what's the probability that that edge is cut, right? Now we're assuming that both U and V are in S, right? Now, for every edge that is neither incident to U nor V, probability is still 1/2. For every edge that is incident to one of them, the probability is still 1/2. The probability, what about the edge between them? It's 0, right? They're both on the same side, so it's definitely not being cut. So if they're both on the same size of the cut, then the expected value is, M/2 minus 1/2, because you lost half an edge, right? Which in particular then means that if they're on opposite sides of the cut, then the expectation if U and V, if V is in S and U isn't, then the conditional expectation is M/2 plus 1/2. Yeah, because that edge is always cut as opposed to never cut. Right? So we should now greedily decide that U is not in S. Okay. Now, okay, let's think more generally. Suppose I have two vertex sets, A and B, that are disjoint, and let me say that EAB is the set of edges that with one endpoint in A, the other endpoint in B. EA are the edges with both endpoints in A, and EB are the edges with both ends in B. Okay, so here is the picture, right? EAB are the ones that go between A and B. EA are inside A. EB are inside B. All right. I'm going to decide that I'm going to define XP of AB to be the expected size of the cut, given that A is in S and B is disjoint from S. Yeah. So here's the picture. Okay, so XP of AB is the expected size of the cut given that A is in S and B is not in S. Then what do we know? So again, let's do indicators. For every edge with both endpoints in A, so for every edge in EA, what is its expectation? 0. The same for EB. What about EAB? It's 1. And for everyone else, 1/2. Yeah? So in particular, XP of AB is nothing but M minus EAB minus EA minus EB over 2. So that's everyone else over 2, plus 1 for every EAB edge. Right? So in particular, notice that for every pair of sets AB such that are disjoint, I can actually compute the conditional expectation quite easily. Yeah. Okay. Now, suppose I have decided that I want A to be in S and I want B to be not in S. right? I've already decided this somehow. And I pick up a vertex that is neither in A nor B, and I want to decide, like, where should I put them? Into A or into B?
Like the edges that have one endpoint in A and one endpoint in B versus edges that are crossing.
So EAB is one endpoint in A, the other one in B, and EA is both in A, EB is both in B. This thing is, I'm taking, this is all the other, this whole term is all the other edges. It's all the edges, like the edges that are neither in EAB nor in A nor in E nor in B. Each one of those are actually random, so those are 1/2. Yeah. Yeah. Okay, so suppose we have already decided that A should be in S, B should not be in S, and I'm trying to figure out what to do with the vertex V. Right? Now I know that, you know, the expected size of the cut given AB is the expected size of the cut given of A union V comma B times the probability that V is in S plus expected size of the cut given that I put V into B times the probability that V is not in S, which is of course 1/2 those two probabilities. So I get this 1/2 XP A union VB plus 1/2 XP A B union V, right? So this conditional or this expectation here is an average of these two numbers, right? Like it's this one is an average of the other two. So it means that at least one of the two is bigger than the average. Right? The largest one of them is bigger. So in particular, that leads to a fun algorithm because we can compute XP of AB, right? We know what it is. So, and in the beginning, with A equals empty set and B equals empty set, XP is at least M/2, right? So now what do? You just go over all the vertices and you ask, should I put V into A or B? You figure out which one gives you the largest conditional expectation. Great. You take the one with the bigger conditional expectation, and the one with the bigger conditional expectation will have bigger expectation than what you currently have, or bigger, greater than or equal to, right? So if you started out with conditional expectation at least M/2, then in each iteration you're still going to have conditional expectation at least M/2. And by the end of the for loop, you have put all the vertices into either A or B, because you decide this on all the vertices. So here's an algorithm that always runs in polynomial time, always outputs a cut AB, and just by induction, in the end, the conditional expectation of the size of the cut AB is at least M/2, but there is no conditional expectation because the cut AB is just, there's no randomness. You've decided for all the vertices whether they go in the set or not. And therefore, you've found a cut of size at least M/2. Yeah. This is what is known as the method of conditional expectation, where you have a randomized algorithm that is making some choices at random, and the expected outcome of the algorithm is good. Then what you can do is you can pick up the choices, the individual choices that the algorithm makes for each vertex to go in or out. If you can compute the conditional expectation for the outcome given a subset of the choices, then you can make the choices one by one and always go towards the greedily better choice. And as long as you can compute what the conditional expectation is, you will in the end up with a set of choices that at least achieve expectation. Yeah. So that's a general scheme. So here's a funny thing. If you actually inspect what the algorithm does, if you inspect, like, if I have A and B, and I'm trying to determine for a vertex V, what happens to the conditional expectation if I add V to A or if I add V to B, then really what happens is that all of the edges from V to A union B become decided, right? Like for them, you now make a decision whether they get cut or not. And for all of the other edges incident to V, they are still probability 1/2 kind of edges. And so in particular, what happens is that the edges from V to A union B, they are split into two parts, the ones to A and the ones to B. The edges to B get cut if you put V into A, and the edges to A get cut if you put V into B. And so you should just greedily choose to cut the most edges at that time. Yeah. So in particular, this conditional expectation algorithm can now be just rewritten like this. Initially, A and B are empty. You go over all vertices from 1 through n, and then if V has more neighbors into B, then you put it into A. If it has more neighbors into A, you put it into B. Yeah. Like here's a funny thing, and of course we now proved by conditional expectation analysis that this will always output a cutoff size at least m/2. But in fact, the fact that this greedy algorithm outputs a cutoff size m/2 has an easy direct proof tutorial. So a question is, okay, like, why on earth did we do this whole randomized analysis if there is this simple greedy algorithm that does the same job? Well, you know, simple greedy algorithms are simple greedy algorithms in retrospect, right? They aren't simple before you see that they're there. And this here, you get like a no creativity needed way of arriving at the correct algorithm. You know, whenever I teach an undergraduate algorithms class, students will always approach me and ask, Professor, this is all very nice, but how do I know which algorithm to use, or like how to make an algorithm when I see a problem, right? And I tell you, well, you just have to do it a bunch of times, and maybe eventually you'll get it. And like I'm just the best way I can teach this to you is by a lot of examples with the hope that you can generalize from it. But in this case, so here is one case where you actually do not need any creativity, right? There are some situations where all you need to do is to see, well, what if I made all of my decisions at random, compute the expected outcome. If you're okay with the expected outcome, then there is a method for deterministically achieving at least the expected outcome. Yeah. Okay. Fine. Okay. We got a simple greedy algorithm for max cut. What about a simple greedy algorithm for set cover? This time, I'm not going to go through the motions of turning the randomized algorithm into a greedy algorithm by method of conditional expectation. I'm almost certain that it can be done. I sat down and tried doing it and ran into some unpleasant details. So I'm just skipping straight ahead to the greedy algorithm because I will need it later. What? No, I will. That is actually something that I'm going to cover. So here is so here. Yeah. So here here's the algorithm. I'm trying to cover my universe U using as few sets as possible. So a very reasonable thing to do is to pick the set that covers the largest number of yet uncovered elements. Right? So initially you set f prime to be empty. While it doesn't cover all the elements, pick the set in F that covers the largest number of yet uncovered elements and add it to f prime. All right. Well, when you're done, f prime definitely covers U, right? And you terminate in polynomial time. So all you care about is what is the size of f prime. Right? Well, I claim that in each iteration of the for loop, at least one set in F covers at least a 1/opt fraction of yet uncovered elements. So that's for the tutorial. Yeah, but believe me that happens. At least one of the sets in F covers at least a 1/opt fraction of the yet uncovered elements, which then means that if the algorithm has gone through the outer loop for t times, it added a set t times to F prime, yeah, then the number of yet uncovered elements is at most all the elements times the ratio that you lose every time. So that's 1 minus 1/opt to the power the number of rounds you went, to the power t. And 1 minus 1/opt is the inequality, e to the minus 1/opt to the power t. So that's n times e to the minus t/opt. So if we pick t to be opt log n, u minus the uncovered elements, so the number of uncovered elements, is at most n to the minus n times e to the minus t/opt, which is at most n to the e to the minus log n, which is of course less than or equal to 1. When there's one uncovered element, you pick one set and you cover it. Yeah. So after opt ln n plus 1 sets, you've actually covered the entire universe. So here is, yet another simple greedy algorithm, simple in retrospect, for set cover. Okay, why did I teach you this simple greedy algorithm? Now you're not going to love this randomized greedy algorithm, the randomized ILP-based algorithm anymore, which was like half the point of this course. Well, because I'm going to need it for this somewhat more technical thing. So we're somehow done with the cute and simple part of the lecture. Now we're going to start cranking a little bit. We have this 2e to the k time algorithm for k path. And now the question is, well, could we get an algorithm with the same running time, but deterministic? Well, we aren't quite going to get that. We're going to get 2e to the power k times a sub-exponential factor. So the exponent is the same. So but don't care about plus lit low, okay? If you remember the algorithm, we had a 2 to the k time algorithm to find multicolored paths, right? So if we had a coloring of the vertex set, and we wanted to ask, does there exist a path that uses every color exactly once, we could do that in 2 to the k time deterministically. And then we showed that a random k coloring will multicolor a path with probability 1/e to the k. So that was the randomized part of the algorithm. So can we somehow substitute this random coloring step with something else? Okay, you think about this for a little bit, and you can come up with a wish list, right? Like you could come up with some sort of dream theorem of like, what if I could do this, right? Then I would be able to avoid the randomness. And here is a fairly reasonable specification for a dream theorem, or at least like a dream kind of object. So I'm going to say that a perfect k coloring family of a universe U, so think of the universe as the vertex set of your graph, is a family of colorings. So each element of F is a coloring of the vertex set with k colors. So I have a bunch of colorings of the vertex set with k colors, such that every set of size k in my universe is multicolored by at least one coloring in the coloring set. Yeah. Suppose someone gave me a perfect k coloring family of the vertex set of the graph. How would you do then solve k path? Yeah, so you take F for every coloring in F. You check whether there is a multicolored path with respect to that coloring. If you found a multicolored path, then that is a path in the original graph, and you found your k path. On the other hand, for every k path, its vertex set will be multicolored by at least one coloring in your family, just because it was a perfect K coloring family. And then when you're considering that coloring, you will discover your path. So that gives you an algorithm with running time, the time to construct F, plus the size of F times 2 to the K polygon. Yeah, that's okay. So we have so now the question is, does such an object even exist, right? Like, it seems like a lot to ask for. Well, okay. What about a naive construction that only uses a lot of sets? Like, it uses a lot of colorings, like n to the k colorings, and takes n to the k time to construct. So this will, let's that not be a tutorial question. Let's ask it right now. How would you make a construction of perfect k coloring families where the size of the family is n choose k? So in particular, for your, if here is your universe, right? If here is your universe, for every set S of size k, I can make a coloring that is private to that set. So it colors the element of that set 1, 2, 3, 4, 5, 6, all the way up to k, and then let's say colors all the other ones 1. Yeah, this coloring multicolors this set. There are n choose k sets, so with n choose k colorings, I get to multicolor the sets. But of course, now I get with this kind of k coloring family, I end up getting an algorithm that is slower than the brute force algorithm for k path, right? It's just like n to the k times this 2 to the k factor. So this is utter nonsense. But of course, notice if you look at this picture, you will realize that, come on, we colored all of the other elements 1, and that is a terrible idea if you're trying to multicolor as many sets as possible, right? Like if I were a little bit less stupid, I would just color like 1, 2, 3, k, 1, 2, 3, k, etc. Right? And just make sure that the set I care about gets multicolored, and for everything else, I smooth things out. Now, this coloring k colors lots of sets at the same time, right? So there is some hope that I can end up finding a family that is much more efficient than just using one coloring per set. Okay. We haven't said anything yet. We're going to have multiple constructions.
Right, but just an example.
Well, this one is just a single coloring, right? Like this, the example that I gave does not give you a family of colorings. I just said the coloring for a set. Yes, it seems a reasonable idea is to use more colors on all of the other guys than just one everywhere, but I'm not analyzing what happens if you do that.
Yeah, the question was how many sets is the single coloring?
Oh no, so one coloring. Yeah, it's something. Yeah, exactly. It's yeah. Okay. All right. So now let's do something funny. I'll give you a construction that there exists a perfect k coloring family of exactly the size we want, like matching the randomized algorithm perfectly, but I don't know how to compute it. Okay, so I'm going to give you a non-constructive proof that a family of the type that I want exists. It's actually constructive if I allow randomness, but that sort of defeats the purpose. So what I'm going to do is I'm just going to select the colorings uniformly at random. So if I want to select a coloring uniformly at random, then what should I do? Well, I should just color every vertex uniformly at random. So what I do, I select my first coloring uniformly at random. I select my second coloring uniformly at random. I select T colorings uniformly at random. And now I hope that I've covered all the sets. And I'm going to prove to you. Yeah, and I'm hoping that I covered all the sets, and I'm actually now going to prove to you that with probability at least 1/2, I covered all the sets. But now, if I always output a k coloring family of size precisely e to the k 2k log n, and with probability at least 1/2, that thing covers everything, then there exists at least one family that multicolors everything. Okay, now let's just look at one set and one coloring and ask what's the probability that this coloring multicolors that set? And that's k factorial over k to the k, which is, we know, at least 1 over e to the k, right? We showed that. Okay, so now if I fix a set and I ask what's the probability that none of my colorings multicolor that set, well, then the first coloring shouldn't multicolor it. That's 1 minus 1 over e to the k. The second one shouldn't multicolor it. That's another factor of 1 minus 1 over e to the k. So it's 1 minus 1 over e to the k to the power t, where t is the number of colorings we're picking. And what is t? T is e to the k times 2k log n. Hey, 1 minus 1 over e to the k is e to the minus 1 over e to the k. That's the inequality. So the e to the k's cancel, and I'm left with e to the minus 2k log n, which is also known as 1 over n to the 2k. Yeah? So for a fixed set, the probability that that set doesn't get multicolored is 1 over n to the 2k. How many sets do I need to multicolor? And choose k, right? At most n to the k. So by the union bound taken over all sets I need to cover, the probability that at least one set isn't multicolored by any of my coloring families is at most 1 over n to the k, which is of course strictly less than 1. So therefore there exists a family of size t. In fact, if I pick a random set of colorings, then that is going to be a sufficiently good family with probability at least 1/2. Of course, I'm trying to do it indeterministically. I don't have randomness. But at least the object that I want exists. Just need to find it somehow. All right. So yes, of course. Yeah, and the intuition for it is you can prove that you can't really do better than the randomized algorithm. Basically by analyzing the thing you asked about. If you fix the coloring, what is the maximum number of sets it could possibly multicolor? That maximum occurs when where all of your color classes have the same size. And now if you divide the number of sets by the number of sets that get multicolored by a single coloring, you see that you'll need at least e to the k many sets. Okay, now a little bit of linear algebra. We'll assume, so what we're going to do is we're going to now construct a k universal family of size k to the k n squared. Okay, so worse than e to the k, but it's going to be useful for later. Let's assume that n is a prime, right? If n is not a prime, just add some vertices until it is. And, you know, there's always a prime between n and 2n. Yeah. So, okay, we'll just assume that n is a prime. And we'll, instead of numbering the vertices from 1 to n, let's number them from 0 to n minus 1. So I guess you can see where this is going. We're going to work mod n. And for fixed integers, or ab from 0 to n minus 1, I will define the function f(ab) to be the linear function ax plus b mod n. Okay? So what f(ab) does is, of course, it sort of shuffles my numbers around, right? Like every every, what's it called, number gets mapped somewhere, right? Okay, now I claim the following, that for every pair, or so for every pair xy from 0 to n minus 1, if I pick AB uniformly at random, then the probability that FAB of x will be equal to y is 1 over n. And this is fairly easy to see because first pick A uniformly at random, then AX will be something, then there is exactly one choice for B that will make AX plus B equal to y. Yeah, so this is equal to 1 over n. Now, the second one is more interesting, that for every pair x1, y1, x2, y2, if I choose A and B uniformly at random, then the probability that FAB of x1 is y1 and FAB of x2 is equal to y2 will be 1 over n squared. In particular, what this means is that if I tell you that some element maps somewhere, then that doesn't give me any information to where any other given element is mapped. It's what is known as pairwise independence. Yes? Okay, so why is this true, right? Well, we're interested in the event that ax1 plus b equals y1 and ax2 plus b is equal to y2 simultaneously, right? So now we can just solve this system, and this is where we use that n is a prime, because now we have now we have inverses, right? And we're using that x1 is not equal to x2, right? Because if it's not, like, this statement is of course not true if x1 is equal to x2, and I ask what's the probability that x1 f of x1 is y1 and f of x1 is y2 simultaneously, right? Like the function cannot map the same element in two different places, right? So I now have the system ax1 plus b equals y1, ax2 plus b equals y2 for x1 not equal to x2. Now I subtract the second one from the first one and get ax1 minus x2 equals y1 minus y2, and x1 minus x2 is non-zero, so it has a multiplicative inverse, right? So I now get that A is equal to y1 minus y2 times x1 minus x2 squared. So I know what A is, and then B is just y minus ax1, right? And in particular, you know, this is a set of linear equations that are non-singular. You can check this, so it has a unique solution. Yeah. So in particular, that means since you have a solution, you know, for every pair, that means that the probability ends up being precisely 1 over n squared, right? You have one option out of n square options that will give you the right thing. And you then, by you know, conditional probability or bias theorem, this tells you that the probability that f of x2 equals y2 given f of x1 equals y1 equals to what? Pardon? 1 by n, right? Still. So which is, so in particular is the same as if you didn't condition. Yeah. Okay. So as a picture, right, what's going on is that when I pick A, B uniformly at random and I apply F, then things get moved around, and knowing the location of where x1 goes gives no information about where x2 goes. Yeah. Okay. Now let G be your favorite function that maps the integers from 0 through n minus 1 and buckets them into k-square buckets that are roughly the same size. Right? So if you have k-square buckets, every bucket should have size n over k squared. Now I picked buckets 0 through k squared, so I have k squared plus 1 buckets. So I can assume now that every bucket has size at most n over k squared, and don't think about rounding errors. For example, setting g of I equals I mod k squared plus 1 would work. But really any bucketing function here with the properties above will give us what we need. Now I claim the following, that the probability that if I apply FAB, like I pick AB uniformly at random, and I apply FAB to x1, and I apply FAB to x2, they will now become some new integers from 0 to n minus 1. And then I bucket them using G. Then the probability that they end up in the same bucket is roughly what I want it to be, like 1 over k squared. Like the 1 over the, because if things were going on completely at random, right? If I were bucketing things uniformly at random, I have k square buckets. The first one goes in the first bucket, then the probability that the second one goes in the same bucket is 1 over k squared. Yeah, and I want to say that that calculation still holds true even when we don't bucket every element uniformly at random independent of the other ones, but where we bucket them according to this funky rule of choosing A, B, and then applying the function G. Right? So, okay, the probability that x1 and x2 go into the same bucket is, by law of conditional probability, the sum over all the places where FAB of x1 could be, right? So I'm summing over all possibilities for FAB of x1, call it y, okay, of the probability that FAB of x1 equals 1, times the probability that FAB of x2 goes into the same bucket that y goes into. Given that x1 went into, given that x1 was y. Okay, you can now, so the first and the second line are the ones we're comparing right now. Right, so the probability that x1 and x2 go in the same bucket are the sum over all integers x1 could be mapped to by f of the probability that x gets mapped to that integer times the probability that x2 gets mapped to the same bucket that that guy y gets mapped to, given that x1 got mapped to y. Yeah, but now the first probability is just 1 over n. The second probability is a conditioned, but we don't need the conditioning because where x2 goes is independent of where x1 goes. So now all you care about is, now this probability is just the size of the inverse of G inverse of y times the probability of every element in G inverse. So that's just the size of G inverse times 1 over n. And what is the size of G inverse y? It's n by k squared, right? It's the size of the buckets. So now this is at most n over k squared times 1 over n. So remember, we're summing over n things. So n times 1 over n cancels, and then I have n over k squared times another 1 over n, and I'm getting 1 over k squared. Okay, so what is the summary of this? The summary of this is here on the picture, that if I pick AB, and then I apply f to shuffle my integers from n minus 1 to other integers in n minus 1, and then I bucket them using my favorite bucketing function, then the probability that any two guys end up in the same bucket is 1 over k squared. Okay. Now, I claim the following. For every set of size k, there exists at least one choice of AB such that G applied to FAB is injective of S on S. Being injective of S means that everyone in S go to different buckets. Remember, I have a set of size k, and I have k square buckets. So I'm now trying to figure out what's the probability that these k guys go into different buckets. No pair of them ends up in the same bucket. And if you've ever analyzed the birthday paradox, it's a very similar analysis to the birthday paradox. So, okay, what we're going to do, let's pick a random AB, and let's count and let's ask ourselves, well, what's the probability that a given pair of elements in S end up in the same bucket? Well, that's 1 over k squared. How many pairs of elements in S are there? K choose 2. It's less than K squared. So by the union bound over all K choose 2 choices of x1, x2, and S, we have that the probability that there exists 2 guys in S that go to the same bucket is at most K choose 2 over K squared, which is at most 1/2. Yeah? So in particular, we know that if I pick FAB at random, then the probability that it's not FAB, it's GFAB. Yeah, so this would be G of FAB is injective on S. This probability is at least 1/2, and therefore there exists an AB such that G of FAB is injective. Okay, let me move this around since I'm already doing it. B exists AB such that G of FAB is injective on S. Okay? So that's what we proved. This almost makes us ready to get a K to the K square sized universal family. Remember what our goal is. It's to make a family of colorings that is not too many of them, and so that every set of size K gets multicolored by at least one of these colorings. Now I claim that if I have a K-perfect coloring family of a universe of size just K squared, then I can get a K coloring family of a universe of size N of just size N squared times H. So H is the coloring family. So in order to get a perfect coloring family for a large universe, but small sets in a large universe, it's sufficient to get a perfect K coloring family for small sets and only not that much bigger universe, right? Like the universe is the square of the size of the sets I'm trying to color. Okay, how do we prove this? Given the perfect K coloring family H for the K square size universe, F will contain a function for every FAB from the previous lemma and for every H in the perfect coloring family. Now, how are we going to choose? So how do I now color every element from my big universe? It maps every element in the big universe to one out of K square buckets, treats the buckets now as integers from 0 to K square, and applies H to color the bucket. So everyone in the same bucket gets the same color. Yeah. Now, notice that F is at most H times N squared because every function in fancy F is indexed by a coloring in H and an A and a B, right? And I can construct it efficiently, right? I may just loop over all colorings in H and over all A and B. And furthermore, now let S be an arbitrary set of size K in the big universe, right? Now there exists some AB such that G of FAB is injective of S, so S gets mapped to some set of size K in the K square size universe by AB. And now when I apply the H that colors the red set with different colors, then of course my original S is going to get different colors as well, right? The S on the left gets mapped to the S in the middle, which gets mapped to 1 through K by H. So for that choice of A, B, and H, S gets multicolored. Okay, so what does that mean? Look at the lemma. The lemma statement is, if I have a K-perfect coloring family for a fairly small universe, one of size K squared, I also get a perfect K coloring family, even for large universes, at the cost of a universe square overhead in the size of the family. Okay, but here is a very simple corollary. There exists a perfect K coloring family of size k to the order kn squared, constructible in roughly same time. And the proof is just the lemma plus the naive n choose k construction, but now n is k squared. Right? We have the n choose k construction. That's a k squared choose k construction, so that's k to the 2k. Yeah, so it's a universe reduction. We're reducing the task of constructing a k coloring family for small sets in a large universe to constructing k coloring family for the same size sets in a much smaller universe, one of a universe of size at most k squared. Yeah. If you're familiar with kernelization, it's kind of like kernelization for k perfect coloring families construction. And as a corollary to the corollary, of course, we get the k to the k time algorithm for k-paths, because you now can go over all of the colorings in this family that we just made and get a every path, if it exists, will be multicolored at some point. Run the 2 to the k algorithm to recognize the path, and you find it. Okay. Ephemeral question: can we do better? Right? We now have a perfect k coloring family of size k to the power k. Can we get one of the same kind of size as our randomized algorithm? So what we're going to do now is we're going to apply something that I call a splitter lemma, which the previous lemma reduced the task for finding a k perfect coloring family from a large universe to a small universe. This one says, if I'm looking for a k coloring family for a small set in some universe, it's actually sufficient to find efficient coloring families for much smaller sets for the same kind of size universe. Yeah. So formally, the statement is the following: for all integers n, the universe size, k, the size of the sets you are trying to k color, and t, some parameter to the lemma, if I give you a k over t perfect coloring family for a universe of size s, so I'm multicoloring all sets of size k over t. Yeah, then I can get a k perfect coloring family for a universe of size n of size at most h to the power t times n to the t. So if I shrink the size of the sets I'm trying to color by a factor t, that corresponds to an exponent of t in the size of the family. And recall that I'm looking for families of size e to the k. So that is a trade-off I'm very happy to make, right? Like if I'm able to find a family of size e to the k over t for sets of size k over t, then when I multiply that back out again by t, this is going to be e to the k, right? I pay a cost. The cost is an overhead of n to the power t. But if n is small, if n is k squared, I'm only paying k squared to the t, and I should be able to choose t in such a way that that factor isn't too big. Okay. Now let me prove the splitter lemma for you. Take the universe and order it. Yes?
Family H.
No, so I'm saying if there exists a k over t perfect family H for universe of size n, then there exists. I mean, the way the notes are written are a bit ambiguous. What I mean if there exists such a coloring family, then there exists such a coloring family, and given H, I can construct F. Well, it's for the same set. The graph doesn't matter, right? We're doing things totally oblivious to the graph we're working with. All we know about the graph is that it's a vertex set of size m. Yeah, like it's for the same size vertex set. Okay, so let's do this. I order my universe arbitrarily from U1 through UN. And each function, in fact, and I'm now assuming that someone gave me H, and I'm now trying to construct F. Yes. Well, yes, but what did we just do? We just had the universe reduction lemma, which says that without loss of generality, n is at most k squared. So if you plug in n to be at most k squared, then you're happy. Yeah? Yeah. Okay. So order the universe from U1 through UN. And every function f in f is defined by a contiguous k partition of u into U1 through UK. Okay, what's a contiguous k partition? Well, what's a k partition? It's a partition into k sets. Contiguous just means that if your universe is ordered U1 through UN, you pick the first some elements, that's U1, then some more elements, that's U2, then some elements, yeah, they're not shuffled together, right? Like you're picking some part, you cut it off, that's U1, some more part, that's U2, yeah? That's what I mean by contiguous k partition. And in addition to the contiguous k partition, I give you a function, or a function hi from the ith copy of the perfect family H for sets of size k over t. So what f, I think the picture shows this better. So what I want to do is the following. I have some unknown set S that I'm trying to multicolor. I don't know where it is, but I know that there is some contiguous k partition that will split my unknown set up into pieces of size at most k over t. Right? I just go from left to right until I've eaten k over t things of the set. Then I keep going from that point to left to right until I eat k over t more things from my set. Yeah. Now the point is I don't know where the set is, which is why I try all possible contiguous k partitions. Now with the knowledge that one of them will be the right one. Yes. And now with the assumption that I picked a contiguous k partition that evenly splits the set I'm trying to multicolor, now I know that in every part I only have k over t elements from my set, which means that I can apply my k over t coloring family H to color that part. Yeah, but now for each part of my partition, I need a k over t coloring. Yeah, so I need, so that's where the h to the t factor comes from, because for each of the t parts, I point to one function in h. That's the function that I used to, like the ith function I'm using to color the ith partition, or the ith part of the partition. So formally, I'm defining f of ui as follows. So ui is an element of the universe. I say, let j be the part so that ui is in jth part, like ui is in the jth part. And I set f of ui to be the jth h function applied to ui plus k over t times j minus I. Where does this k over t times j minus I come from? Well, if h1 uses colors 0 through k over t, right? h2 uses the colors 0 through k over t. So if I use h1 to color u1, h2 to color u2, h3 to color, they're all going to be using the same k over t colors, right? But I don't want this color collision. I want to use all of my k colors. So I want h1 to use the first k over t colors, h2 to use the second k over t colors, and so on. Yes, which is now formally handled by saying that f of ui is k over t times j minus 1 plus hj of ui, right? Don't look at the formula, right? Like just if you are in the jth part, then you are using the jth set of k over t colors. Yeah. Okay. Now, what is the size of f? Well, it's n to the k over t, is it n to the, no, it's n to the t, right? Because I'm using, yes, it's n to the t because I'm choosing t parts. Times h to the power t, yes, which are the choices for which function I use for the tth part. And now consider any set S in the universe of size k, there exists a partition that evenly splits that set. And for now, let h1 through ht be the function in h such that hi is injective of S intersected with the ith part. Yeah. Then, of course, the corresponding function f is injective on S. Yeah, because what's going on here is that S is evenly spread out, right? S is evenly spread out among the among the t parts. Now, in each t parts, it got rainbow colored. Let's see if I can rainbow color things here. Right, it got rainbow colored, rainbow colored, rainbow colored, rainbow colored. And now for each part, we're using different colors of the rainbow. So there's no color crashes between different parts. Only have 5. I think screen recording is expensive on power, and I might. Okay, I'm going to have to plug in, unfortunately. I think I have a charger. Let's see. There we go. Hopefully this will last us for a little bit. Well, it should be okay. I mean, I only need to last for another 20 minutes. So, okay. So, what does this do? Right? We have now proved the splitter lemma. Right? We've now proved that if I can give you a k over t perfect coloring family H for a universe of size n, then I get a k perfect family for the same universe size but much bigger set. So I can now reduce the task of finding k coloring families. I can reduce the task of finding k coloring families for a, small but not that small set, to the task of finding perfect coloring families for much smaller sets in the same universe. Why is the same universe? Because each individual part of the k contiguous partition could, for all you know, be almost the entire universe. Yeah, I mean, you expect it to be about universe over k, but or universe over t, but it could be everything for all you care. Okay. Now, let me give you the scheme for the final thing. Okay, here we go. I'm trying to multicolor some hidden set of size k in the universe of size n. Right? Let me apply universe reduction, so that now at paying a factor n squared, oh, what did I do? Can I do this? Ah, okay. Paying a factor n squared in the size of the family. So green is what I pay in family size. Okay. Blue is what I do in order to get there. So paying a factor n squared in the size of the family, I now reduce to the task of k coloring a k size set in a k square sized universe. Yeah. Now applying the splitter lemma with a carefully chosen t, I'm going to set t to be k over log square k. The reason it seems like a strange number, but the reason will become apparent in a little bit. I am now reducing the problem of k coloring this set in the k square sized universe to finding perfect coloring families for sets of size log square k, because k divided by k over log square k is log square k, in the universe of size k squared. Yeah. And now what is the cost? I paid an overhead of size n to the t, so that's k squared to the k over log k. That's a sub-exponential factor. I'm very happy to pay a sub-exponential factor. Yeah. Remember, k to the k square is also known as 2 to the power 2 log k. Yeah. So 2 to the 2 log k times k over log square k, I get 2 to the k over log k. So that's sub-exponential. Yeah. So this I'm happy to pay. Now, for each one of these, I'm multiplying them together. That's the h to the t factor. Yes. And now I need to find a k-perfect coloring family for each one of those. What do? Let me do universe reduction one more time on each one of those. Yeah, because I can. Also, for each one of them, remember, what do I pay? I pay a k square factor. Yeah. Well, what is that going to cost me? I'm going to pay k square again to the power t. So that's the same factor here all over again. So that's another sub-exponential factor. So I'm happy to pay it. Yeah. So now all I'm left with is I need to find a perfect k coloring family for these tiny sets. Yeah. Okay, so I reduced my problem to essentially the same problem, but with much smaller values of k. Why is this good? Well, I know that that such a family exists. I had this existential proof that says, like, well, if I'm looking for a set of size log square k perfect coloring family, then there is one of size e to the log square k. I couldn't find it before because, k was big, but now I can afford to spend time like c to the k. I can afford to spend time 2 to the k. But the parameters that I'm playing with now are way smaller. They're like polylog k range. Yeah. So now I can afford to do crazy brute force style kind of things. Yeah. So what is it I'm going to do? So I already did this analysis. Like, suppose I am able to find a family that is only slightly larger than what I know exists, right? Instead of e to the log square k times log k, I will find something of size e to the log square k times log to the 5k, right? Suppose I'm able to do this, then you multiply together all of the green things you saw up there, and you'll see that what you will end up with is precisely e to the k plus little of k times n squared. I mean, I've already done this exercise. I'm not going to do it again. I don't think it's particularly insightful. When you just multiply all of the things together, you see what you get, then it's the right thing. Okay. We have one more thing left to do, namely finding a log square k perfect coloring family for a universe of size log to the 4th k, and we want to do it mildly efficiently, right? We don't want to use more than e to the k time doing it. It comes from the base case powered together t times. Yes. And here's the idea, and which is why I told you the set cover approximation algorithm. We're going to reduce the task of finding a k coloring family to the set cover problem. In particular, I'm going to take the sets that I'm trying to color. They are going to now turn into elements. Oh, this is the crazy. Okay, so I have a universe of size log to the 4k. And in it, I have sets of size log square k. So for every set of size log square k from my universe, I have an element. Yes, this is what, like, now I'm describing how to find. I'm now describing how to find a perfect log square k coloring family for a universe of size log 4th k. Yeah, in reasonable time. And now we're going to do something. Yes, no.
Apply the same reduction.
We can. The point is that, like, every time you do, you pay some overhead, and you have to make sure that you don't overpay on the overhead. And for slightly more complicated constructions of the pseudo-random objects, you actually want to apply it a few more times. So if I had done what I had originally planned to do in this lecture, I would have to do this to level 4 or something, like to log or something. But I decided that this was complicated enough. For this instance, we're going to find a family that is almost as good as the existential one, right? Like the existential one says that there exists one that only has e to the log square times polylog k for colorings. And we will find e to the log square k times polylog instead of polylog log. Yeah. So, okay. Here we go. We have a universe of size log to the 4k, and in there are sets of size log square k. For each set of size log square k, let's make an element of our set cover instance. How many elements are there? Well, not more than 2 to the power universe size. Yeah, that's a gross overestimate, but I don't care. For every coloring of the universe with log square k colors, I'm going to have a set. How many sets do I have? Well, not more than k. Actually, not more than, log square k to the power log 4th k. But again, I'm going to be lazy, not more than k to the log 4k, many colorings. And now a set corresponding to a coloring contains an element corresponding to a set if the coloring multicolors the set. Yeah. So if it's too overloaded by that I'm using sets for sets and sets for colorings and colorings for elements, yes, just think of this as a bipartite graph. Yes, I have sets on the top of the bipartite graph. I have colorings at the top, sets at the bottom, and I have an edge from a coloring to a set if the coloring multicolors the set. That's what happens. Yeah. And now what is it I'm trying to do? I'm trying to find the smallest number of colorings such that every set is multicolored by at least one of these colorings, which is the same thing as saying I'm trying to find the number of green sets such that their union contain all of the red elements. Yeah? But I know from the existential proof that there exists a log square k perfect coloring family of the size e to the log square k log to the 4th k, right? Like I know that exists here. Yes? That means that there exists a set cover of that size. Yeah? Which means that the greedy approximation algorithm that just runs in polynomial time in the size of that input instance will find one of size opt times the logarithm of the universe size. And what was the universe size? The universe size was 2 to the log 4th k. The log of that is just log 4th k. Yeah? So I'm now getting just a log 4th k additional factor in my approximation ratio, which means that what I found was a set cover of size at most the right thing times log to the 5th k, and this set cover corresponds to a log square perfect coloring family of size e to the log square k times log to the 5k, and I'm done. To conclude, we can construct k-perfect coloring families of size e to the k plus little o of k times n squared in time about the same time. It takes the size of the time it takes to construct the family is proportional to the size of the family, roughly. And this does give a deterministic algorithm for k-paths with the same running time as the randomized one. The same scheme, universe reduction plus universe reduction plus splitters has been used to de-randomize a number of randomized algorithms. Like basically, anytime you have some hidden pattern of size k in the big universe of size n, and you only care about what happens to that pattern, this is a good thing to try. Using the same kind of methods, we can de-randomize the counting thing. The thing that you need to care about there is that now you need not only, so instead of perfect coloring families, you, for every set, you don't not only want it to be split at least once, you want every set to be split by roughly the same number of colorings. Yeah? And that can be constructed in a similar manner, but now the problem you're solving at the bottom isn't quite set cover. You need to do some more complicated probability analysis of your FAB functions. So I don't want to go there. And with that, let me conclude. Thank you. Yep. This diagram or the previous one?
So shouldn't the being like the k-square thing? I was wondering whether because earlier it was n and the cost you were paying was n squared. Here the universe size is k square.
Oh, it should be k to the 4. Yeah, yeah. You're right. Yes. Yep. So let's make it more wrong before we make it better. There. Thank you.
I'm assuming it doesn't matter.
Yeah, it doesn't. I mean, the calculation of k squared to the k over log square k and k to the 4 over the k over log square k gives you the same thing. Yeah.
Like the same universal reduction number of times. What would have changed?
So I mean, what happens is, I mean, you need to iterate. So you can't just keep applying universe reduction, because what universe reduction does is it brings the size of the universe down to the square of the set you're trying to color. So keeping applying universe reduction after the first universe reduction doesn't do anything. So you need to do universe reduction splitter, universe reduction splitter, universe reduction splitter, because what splitters does is to keep the size of the universe, but splits the set into tiny pieces. Right, so it keeps the universe the same, but makes the set smaller. Yes, exactly. But you can only, but splitters only work when the universe size is already small because of this, because of this n to the k over log. I mean, you don't want an n to the k over log square k factor. You want a k to the k over log square k. So that's why you apply universe reduction before you can apply splitters. Right? Like what you really want to do is to just apply splitters, but you can't. So you need to do universe reduction first.
Talking about